they're claiming they can build like concepts.
Now I know.
I'm not sure. It's two-dimensional. So there probably is a range to scale. There obviously is, but I don't know what that is. Depends on how long it's
You can't go and say.
But nobody's proved that. So if anyone did.
Was it Julia? Yeah, she was on my phone. So, speaker. Sign.
Hello? Hello? All right, thanks everyone. Just wanted to welcome you all here to Netflix. My name is Justin Basilico, and I lead the page algorithms team here at Netflix. So now if you if you see some bad recommendations on your homepage, who you have to blame. We're really excited here to have the San Francisco Big Data Analytics Meetup hosted here at Netflix for the first time. And since it's our first time hosting, I did want to talk a little bit about why Netflix is interested in the machine learning space in hosting talks like this. Of course, for most people, when they think of Netflix and machine learning, the first thing that comes to mind is the Netflix Prize in doing movie rating prediction. But that was from when we launched back in 2006, and when Netflix was primarily a DVD by mail company. And nowadays, we're of course an instant streaming service that's available internationally, and even started producing our own original content. So our approach to recommendations and personalization has obviously changed a lot since then. And it's gotten to the point now where we try to personalize as much of our site and our user experience as possible. So about 80% of what people watch on Netflix comes from our recommendations. And the reason that that's relevant for this type of meetup is that those recommendations are all powered by machine learning. We also use machine learning in other parts of our business, such as trying to figure out what content to buy or to produce, and also looking for what devices or if there's fraud and anomalous activity on the service. So we end up doing a lot of applied research in the machine learning space, and are always looking for great new people to come and join us. So if you're interested, come and see either myself or one of the other Netflix colleagues after the talk. Of course, in the space of machine learning, I think our speaker needs very little introduction. So I'm very happy to welcome Jure Leskovec, who's an assistant professor of computer science at Stanford, as well as a chief scientist at Pinterest, which he joined after his startup Kose was acquired earlier this year. Jure is most well known for his groundbreaking research around applying data mining and machine learning models to graphs and particularly large-scale social networks. But today he's going to be talking about an application of these techniques in the recommendation domain and tackling one of the core problems of recommendation, which is around similarity. So please join me in welcoming Jure.
Okay, great, it works. Hello, very happy to be here, and thanks for having me. And what I plan to do today is tell you something about basically what we started doing at the startup I co-founded more than a year ago, and then how what we are doing kind of transfers to Pinterest, and it's all around recommendation systems, machine learning, trying to understand how different types of items, objects fit together and how they relate to each other. And it will become clear why Pinterest wants this, and I'll show you how we do this, and there's even a paper you can go and read about. So first I'll educate you what Pinterest is, right? So the way Pinterest really thinks about itself, it thinks about itself by that it wants to connect people with objects, right? So the way we think of the product is that we wanna have a rich set of objects. These objects, I'll show you later, are called pins, and we wanna connect people with those pins. So one way to think about Okay, good. Yes. So one way to think about the whole problem is the following, right? We have these Pinterest users, and the way they use Pinterest is basically to go, they are almost like human spiders who are going on the web, and they are saving objects or content that is interesting to them, right? And this way, Pinterest is kind of nothing else than a visual bookmarking website, right? But bookmarking, so basically saving, is not the only thing it does. As people save things into collections that I'll show you and I'll talk about, then they can also go and discover these things, and after they've discovered these objects, they can actually go and do something with these objects in the rest of the web, right? So in this respect, Pinterest is a way for you to kind of bookmark interesting things you see on the web, save them, curate them, search them, retrieve them, and then go back to the web and do something on the web of Pinterest. Okay, so just an example, right? The objects we are talking about are called pins. Pins are defined by images. Pins usually have some description, and then we also and they have more. They also have some additional information attached to them, right? So this is a pin about a recipe about a blueberry crumble, right? So it's not just some image, but it's actually quite heavily annotated image with lots of information about how you can go and prepare this delicious dessert to yourself, right? So this is an example of when I say pins are rich objects, right? And now if I have these pins, these objects can be organized into collections. These collections we call boards, right? So basically, a person can say, these are the things I'm interested in, and kind of organizes these objects in its own sets of collections, right? And this is an example. I think she's a mother and a photographer, so she's like organizing, the photographies she did in these various kinds of boards, collections of her favorite photographies, newborn posing, things like that, right? So basically, and when Pinterest really works is it works when people need ideas. When you're like, I want to do something, I wanna go shop something, I want to build a tree house and I need an idea, you will kind of get these ideas on Pinterest because there are people who put together boards and said, my favorite tree houses, the way how, my favorite newborn posing postures if you want to take a picture of your newborn and so on, right? So it's really more than just a bookmarking service. It allows you to also discover new things, get ideas, and then act on those ideas, okay? But right, the same way as individuals can do this, can create these boards, the same way businesses can create these boards and kind of go and start engaging with their followers and their customers and so on. But the point is kind of the following, right? We have around 30 billion of these pins, and we have 750 million boards, and more than half of these pins have been created in the last 6 months, and it's all kind of a big mess, right? We just have these pins, and the question is, how do they start fitting together? Could we kind of start to model relationships between these pins? And the reason why we may want to start model relationships is because we want to make recommendations to our users, right? We want to be able to recommend people, I'll show you examples later, a given object, and also explain how it relates to other objects so that they may kind of go and explore and we give them good contextualized recommendations. Okay, so what do I want to focus on this talk on is really this question about how do I go and uncover the relationships or the network of relationships between pins, or how would I go learn a relationship network between objects. Okay, that's what I'm trying to do. So I'm trying to kind of understand how this set of objects, how do they fit together? How do they relate to each other? That's what I'm trying to do. Okay, so on Pinterest, it's kind of what my objects are. They are my pins, and these pins can live in different boards. They can be pinned by different users. The same pin can appear in many different collections. Collections can be shared with each other, and so on. And what do I really want to understand is how do these pins fit together into some graph structure that I can use to give me context for recommendations. I can use it for allowing people to browse it and things like that. Okay. So just to kind of give you an idea how everything fits together from I guess data model, the way we think of this is we have a set of pins. Pins belong to boards. Each pin can belong to multiple boards. Each board belongs to a creator. A person can have multiple boards. A given pin can belong to multiple boards. And these pins each pin kind of points to a web page, right? So each pin also has a link. So we also know how these pins are pointing back to the underlying web graph, right? So that's kind of the levels of complexity with which we are working. So these are the basic objects. They are organized into playlists or boards, whatever. We have users, and we have the underlying web graph to which these pins are pointing. And most of these things are kind of many-to-many relationships, okay? So what do I want to do, right? What I want to do is kind of go and understand how my pins, how my objects fit together. And I'll give you a very concrete example now. Rather than just talking in general about pins, I'll start focusing, narrowing down, and just talk about products, okay? Because it's kind of easier to think about, and it will be clear how you can generalize this beyond products. But what I'll talk to you about today, I'll talk about how do you figure out how products relate to each other, okay? And on Pinterest, many pins are products, but we have also pins about locations and other things, and we can also start thinking about how locations fit together, and I'll give you some examples to the end of my talk. But for now, let's just limit ourselves to products. Let's limit ourselves maybe, to products you can buy at Target.com or Amazon or whatever, right? So just a set of items. And how will I start thinking about this, right? Imagine I give you a huge product catalog. I have tens of millions of products. And I give you all the data I have about these products. I give you the reviews. I give you the product description, all the characteristics, all the kind of the information about the properties of the products, prices, brands, anything you want, right? And what would I like to do is now I would like to figure out how these products fit together. How do they kind of relate to each other? So what do I want to do is I want to start predicting whether two products are related and in what type of relationship they are. And again, I'll make this much more precise. But just to give you a bit of a preview, what we will be doing is we'll be kind of wanting to do the link prediction. I want to predict how two products are related to each other. We will use some kind of topic modeling. It will become clear why, and we'll be exploiting product hierarchies. So these are kind of three components of the solution that you are going to see next. But now, what is that I'm really trying to do, right? So what I'm really trying to do is I'm trying to predict relationships between my objects. And as I said, for the purpose of this talk, let's focus only on products, right? So if I say I want to build relationships between products, there are two types of relationships, again, we'll focus on for this talk. You could think of other types of relationships. For objects that are more than products, you could also think of even more types of relationships. But if you just think of the products, then there are two types of relationships that first come to mind, right? One is what you call substitutes. This would be products that kind of can be substitutable, are kind of substituting each other, right? These are almost like products that are competing, right? If I have a vacuum cleaner, then other vacuum cleaners are substitutes, right? While I also have this other type of a relationship, which is a complement, which is, the vacuuming bags go together with the vacuum cleaner. Right, so I can start thinking about, I have objects and right now, I just defined two types of a relationship. I defined a substitute relationships and I defined this notion of a complement, right? Like something that goes together with the vacuum cleaner, like vacuuming bags, extension cords, things like that, right? So this is, filters, I don't know, right? So these are the two types of relationships that I will wanna learn. And everything I'll show you is kind of independent or works for any kind of relationships you wanna define. You just have to give us a few examples of those relationships. And again, depending on the application, those might be different things. For products, here are two examples, okay? And I'm not just good enough to learn these relationships, I will also want to be able to explain them, right? So I want to be able to say that one vacuum cleaner relates to the other one, and that one is quieter and cleaner. The other one, maybe cheaper and higher power. Things like that, right? So I want to be able to somehow explain or give some explanation, surface it out about the relationships between these objects that I'm trying to learn over. Okay, so how to think about this? Again, just focusing on products, I can think I have substitute products, right? This would be, all the dresses, all the shoes, and you would imagine that these are things when people are in browsing mode, I could make these recommendations because they are looking at a particular product category. But then, for example, I could then maybe want to also have the complementary relationship, which is after you decided to buy shoes, now I can start saying, oh, I want to show you the matching dress, right? So that's one idea how you may want to use the network. I'll show you more ideas later, right? But the idea is that I want to kind of uncover, rather than thinking of this as kind of unstructured, I want to really try to uncover what are the relationships between these objects. So why do I want to do this? What can be this used for? So the first thing is I want to understand what are these two notions? What's the notion of a substitute and of a complementary good, right? Like what can be substituted for what and what can be complemented with what? Another thing that this will allow us to do is it will allow us to explain or generate explanations why certain products are preferred over other products, right? So we'll be able, because we have data about how people talk about these products, this will allow us to extract sentences, short phrases that we'll be able to highlight or, with some human curation, clean up, that will allow us to explain the relationship. So that's the kind of the second thing. And the third thing that is kind of very important is because if I know how things fit together, then I can start making these kind of very, very interesting recommendations where I say, these are actually real examples, so that's why you see it's not perfect. But still, right, if I say, here's my query, I can then say, here are the complements that go together with that query. And I could even, if I think of products, I could say, find me the best shoe that goes with this, and this is a cycling shoe, so it wasn't the best thing, right? But I give you the pants and I give you the shirt. Maybe, this is like good for a young San Francisco hipster type recommendation, right? When they have the fixie, right? But you get the idea. Or you say, here's the product I'm looking at, and I can almost like automatically generate you the wardrobe. I say, here are the things that go together with this, right? These are the products that complement it, and if you have a bag, then you need pants, you need a blouse, and you need shoes. And I'll find you things that complement that are from these parts of product categories, right? So I can do interesting types of recommendations with this, if I know how products fit together. Okay? So what do I want to do? In some sense, what I want to do is I want to build networks from product information. And the way I'll think of product information, I'll think of it as a big document. Okay, so anything I know about the product, I'll just think of that as a big set of words or a big set of features attached to that product, to that object, right? And what do I want to do in this talk? I want to talk about how can we use product data to learn relationships, or how do we use object data to learn relationships, and then also how can we go and actually explain why certain objects are preferred over other objects, right? Can I kind of go and explain relationships? I'll set up the problem, I'll show you 3 solutions. The first 2 of them won't work, but the third one will. But with every step, we will learn something, and this is kind of how we learned how to do this, to our own peril or something, right? So this is the learning process we went through when we were figuring this out, right? So what do I want to do? I want to build a very simple predictor, a very simple function that takes a pair of products and returns me the probability that they are related. Right? And because we have 2 types of a relationship, we have a substitute and we have a complementary, I would want to go build 2 functions like this. Okay, so I give you a pair of products, and the function returns a value between 0 and 1, where 1 means these 2 products are certainly related, and 0 it means I think they're not related. Right? And I would now go evaluate this function over all pairs of products. Already kind of a question mark there, right? How would I go do that? But I can at least talk that I can do it, right? So I go do it, and I would basically do the graph, right? Then if I have multiple of these functions, then the problem starts becoming, what if 2 functions say, I think this is substitute. No, I'm more sure it's complement, right? What do you do in these kinds of cases? So we'll come to that as well. But what do I want? I just want to build a simple function that returns me a probability of something being related. So how do I learn this, right? The way I could learn, I can think of this as a simple, let's say, logistic regression, that I will give it a set of examples of what complements what. I'll give it a set of examples what is not complementing, right? I give you pairs of complements, pairs of non-complements, and I would go learn a classifier. How would I go this? I would say I want to find my set of parameters, and I would maximize some likelihood function that says over all the pairs of products x, y that are related, I want to maximize the probability of that that they are related, and over all the pairs of products that are not related, I want to maximize 1 minus the probability of them being related, right? Just like a very simple kind of log likelihood over all the positive examples and over all the negative examples. So kind of over all the edges of my network, all the relationships, and all the non-relationships in my network, okay? So this should kind of all be very much straightforward, right? So now, how do I build this function? I told you before, I will think of each product as being a big document, and I throw in that document the reviews, I throw in product description, I throw in all the product information, price, anything you can think of, right? And I can represent this as kind of super long bag of words vector. Most of it will be filled with zeros, but there will be a non-zero value here and there, right? And think of this as 100,000, 1 million, whatever, right? And what could I do? I could now, for example, build a function that says how likely are x and y to be related. This will somehow depend on the distance between the two feature vectors, right? Here I'm just taking Euclidean, doesn't matter, and I'm also kind of trying to learn how to put weights on different coordinates or something like that, right? So I could just go and figure out and learn a similarity function that I would kind of train in a way that things that are related, they should be more similar, and things that are not related, they shouldn't be similar, right? You can think of this also just as, let's say, learning a logistic regression on the vector of the differences of the pairwise differences between features. Right, and as I said before, I could even figure out something and say, certain coordinates have to have this weight, certain other coordinates have to have that weight, and that would basically tell me that to be complement, you have to have these coordinates in common, to be supplementary, you have to have some other coordinates in common, okay? So this would be all good. But what turns out to be a huge problem is that these vectors are super high dimensional, they are super sparse, so I overfit like crazy, right? And kind of I'm working with the data at a too fine-grained level of resolution, so I cannot really learn anything from it. It's very hard to generalize from a few links that I have to the whole graph, right? Because I think I think of the problem as having a few training instances, but I have to generalize to kind of the n squared training instances, where n is the number of examples I have, right? I have to be able to predict every possible a relationship between every possible pair in my network. So I cannot really go do this. So now, if this doesn't work, right, what do you want to do? You want to go and do some dimensionality reduction, right? You want to go and apply your favorite kind of method that will reduce dimensionality of your vectors. And one of favorite methods when you work with text is LDA, the latent Dirichlet allocation, right? And the way you can think about this, it will take some documents, some vector of words, and right, and it's not only the reviews and the description, but it can be the price, can be the brand. You just create this kind of long feature vector, and you do dimensionality reduction. And the way you can think about this is that rather than thinking about my product now as this super high dimensional vector, I can think of it as some small dimensional vector in this smaller dimensional space. And think of this space maybe as 400, 1000 dimensional, something like that. We'll train topic models, I'll show you later how, that have 10,000 dimensions or so. But I can now kind of project this down and think of my little shoe as being a point in this lower dimensional space, and I'm able to associate every of the features with a given coordinate, so I can actually start thinking that these are topics that are somehow annotated and so on. Okay? So what have we done? What we have done with this topic modeling approach is that we took our long vector and kind of shortened it, right? So the other thing we lost was kind of, in general, we lost sparsity. So now all the coordinates of this vector are generally filled, but the coordinates now represent some kind of concepts, topics, something much thicker, not so fine-grained. And I could go and apply the same old idea as I had before, just now the number of parameters I'm learning is much smaller because the number of coordinates here is much smaller. And this is the right track, but the problem with this is that this thing will find you the subspace that is able to explain the way the features of the products and will do nothing for link prediction, right? So the problem with this is that, yes, you are modeling the features of your products, great. But what's the problem is that you don't care about modeling features of the products. You care about figuring out the relationships, right? So the question is, what can we do, right? And what do we do is our goal is to learn good topics, but not topics that are good to explain the product properties. We want to learn topics that explain the graph structure. Okay, so I wanna bias, if you want to think of it this way, or kind of push my dimensionality reduction to be able to explain the relationships and not necessarily just the product properties. Okay, and now I want to show you how we do this. Okay, so what do we want to do? We want to simultaneously do two things. I wanna find the embedding of basically the topic memberships of my products so that I can explain the properties or features of the product. But at the same time, I want this embedding to be good also for link prediction, right? So for link prediction, I'll be using some, let's say, logistic regression that will take the latent positions of my products and will ask, are these two related or not, right? So I want embeddings that are good both for link prediction as well as for explaining properties of my products, okay? And I want to kind of do both at the same time. I want to learn both simultaneously. So when I say I wanna learn good topics, what I mean by that is that conceptually I wanna learn to project my products into some small dimensional topic space such that related products are kind of positioned nearby in this space, right? So intuitively I want the distance between different positions to be small, okay? So how do I do this? The way I will do this is the following, right? I will want to learn some set of parameters. This will be my topic memberships. But what I really want is I want to maximize both the likelihood of being able to predict relationships between products and also to be able to model the features of my products, right? So basically the reviews, the product description, things like that, right? So what this means is I want to go and figure out what are the topic memberships, what are the latent positions of my products, such that the topics are good for features for link prediction, right? So I want to be able for topics to explain the features, but also I want them to be able to predict links, okay? So that's essentially the idea. And this seems quite good. This is just more details. Sorry if I'm kind of too detailed, but all I'm doing is this probability of a product given the parameters. This is basically the LDA, the standard latent Dirichlet allocation, and my link probability is nothing else than a logistic regression, right? So it's kind of the simple thing, but the point is I'm training both of them at the same time. What I'm figuring out here is what are the topic memberships, but then up here I'm learning my logistic regression based on the topic memberships of the product I and the product J. Okay, and I have k topics 1 to k. Okay, so simple. I want topics to be able to explain product properties, and based on the topics I want to be able to predict links, and I want to find topics that are a good compromise between link prediction and explaining the properties of the products, okay? So this seems like a good idea, but there are many fixes you need to do to it to actually make this work. So the first problem turns out to be is that relationships are not symmetric, right? It's not that X and Y are related. When we look at products, kind of we see that some things are related, but we also need to learn the direction of the relationship. So it's not just saying are X and Y related, but is X related to Y and is Y related to X. So we need to account for directionality. And what we do is we actually learn two separate models. We learn a model for relatedness, and we learn a model for directedness, right? So the first model is the one I was saying before, are X and Y related, but then the second one we learn, it's basically a different logistic regression, and there's some interesting details, is that the other one that we learn is then, given that they are related, does the edge follow from X to Y, or does the edge follow from Y to X? And actually, you train these two on different feature vectors. So this one you train on the x minus y feature vector, while the direction you follow on x times y feature vector. And this turns to be important because here you are asking how far away are these two products in the topic space, and for the direction you are asking, do they have membership to certain topics, do they share that or not, right? Because you are multiplying. So you want to do it this way. And what is interesting, what comes of it, if you look at what the model is speaking in terms of the properties or the language that people talk about these products, is that relationships are explained by kind of property type words, right? Like words like baby, pajamas, pants, colorful would have high weights in terms of determining the whether there's a relationship. But then the directedness kind of picks up this subjective qualitative language. This is when you look at the models, you get to see this, right? This kind of things like true size, fits well, you know, it's the same color as in the picture and things like that, right? So kind of you focus on different part of the description of the product by doing this two-step process. First determining relatedness and then deciding whether it goes one way or it goes the other. And more details in the paper, but this was an interesting one. The other one that's interesting, I alluded before, which is you really want to learn all these relationships simultaneously, right? Two products cannot be substitute and complement at the same time. So the question is, how would I actually go and somehow make sure that my graph is consistent? And the way one could go do this is kind of fit two independent models, and then maybe you would go learn both at once, right? So this would kind of give you more data on which you could train the model. But what would be the problem would be in terms of that you could have some interpretability, but the problem would start to be that you are kind of training separate things and you are having separate embeddings for different types of relationships. So what we actually decided to do is not train two separate topic models or two separate embeddings for each relationship type, but do it at the same time. So we only learn one embedding, but then we learn multiple different classifiers for each relationship type. So this means that features you discover for products are the same across all the relationship types, but the classifiers you learn to predict an individual relationship, obviously those are different. And this is nice because this means you embed products in one latent space, and this latent space is good for predicting any kind of relationship. So that also turns out to be nice because it gives you kind of only a single set of topics to worry about, and this also helps you with interpretability and being able to explain the results. So that's, right, as I said, one regressor per edge type, but you have one model, one topic model for overall the edge types. And then the last model, the last issue I want to talk about is, if you do it this way, you still have far too many parameters, right? Because I would really want to go and really learn these fine-grained topics over millions of products, okay? So how do you go solve this one? Kind of how do you now make this work? One idea that you can use if you work with products is you can use product hierarchies, right? So you can go and for every product, where in this product hierarchy the product belongs to, or in which parts of the product hierarchy the product belongs. It could be in multiple parts, it doesn't really matter. So what do we do? The idea here is to use category hierarchy to sparsify the model. And let me explain what we do. I think this is it's a cool trick and lots of good stuff comes out of it. The idea is simply the following. This is supposed to be a charger, like a laptop charger, and this is the flattened hierarchy, right? I took the tree and I flattened it out. And this is my topic vector, okay? And this laptop charger belongs to electronics, computers, laptops, accessories, chargers, okay? And then what do I do is, to every node of my hierarchy, right? You see this is a tree, it's just kind of, I flattened it out, right? I kind of laid it out from left to right. With each node of the tree, I associate some small number of topics. Imagine 10, 20, I actually do this in a kind of adaptive way, as I see that I need more topics at a given node, I would attach more nodes to more topics to the node. But the idea is that if I want to figure out what topics this particular product belongs to, I don't need to determine what's the probability that this particular Apple charger, laptop charger belongs to baby diaper category, or to the women fashion category, right? Because I have product hierarchy, I can just ignore all those topics. So what's the point? The point is when I'm estimating the coordinates or the topic memberships of this product, all I have to look at is at the small subset of topics that are associated with the nodes of my hierarchy to which this given product belongs to. So in some sense, I'm learning these topics in a hierarchical way, right? Because if there is another laptop charger here, it will kind of belong to the same set of topics. But if I have a laptop which will share the electronics and computers topics with this charger, but then here in laptops, it will have its own little part. So what this will allow me to do is, up here the topics will be very general because all the electronics products belong to this set of topics, while down here I have this super specialized set of topics that are only for chargers. And down here, I'm only explaining variability that is not already explained by other topics. So what this allows me to do is, it allows me to kind of discover super small, fine-grained clusters of products. It allows me kind of to discover what we call micro-categories, right? Kind of products clusters that are tiny, but they're of super related products, right? So this is what we can do with this, right? So the idea is that up here in the higher part of the hierarchy, I have these very general topics that are describing everything below them, while here towards the leaves of the hierarchy, I have a very specific topics that kind of get learned. And what this buys you by definition, it buys you a lot in terms of scalability, right? So rather than trying to figure out topic memberships of a given object to 1,000 or 10,000 topics, you need to do it to a few tens, maybe 100, right? So you kind of gain much in terms of scalability because you don't have to do as much sampling to determine the topic memberships or whatever. So this is a kind of a small trick, but it turned out to be very important, and it gave us lots of good stuff. So how do we train this thing now, right? So I said before, I have this part of the likelihood where I'm training the logistic regression models, and I have this other part where I'm training the topic models. And the way we do this kind of EM type coordinate ascent idea, where in the what we call the M step, we are training the link predictions, right? You say, given that I know the topic memberships of products, I want to do the link prediction. As I have the predicted links, I can now go and sample topic assignments and basically go and refine the locations of my products and their memberships to topics. And kind of, I keep going back and forth, and at the same time I'm learning the logistic regressions, and I'm training the latent space embeddings or the topic memberships of my products. I won't go into more details. I had 2 slides, I hide them, and there's a paper which you can go read to figure out how this is doing. But the point is, what I show you here is, rather than showing you results on Pinterest data, I'll actually show you results on the data that you can actually go and use. So I'll show you data on the entire Amazon product catalog. So around, I think it was around 9 million products. We have nice user data, so we have nice product review data. So we had around 20 million users, 144 million reviews. And what is nice about Amazon is that they have one type of data that we don't assume in this model. They have behavioral data. They see how people browse products, and they see how people co-purchase products. So Amazon kind of gives us ground truth for some of these labels, right? Amazon says people who viewed X also viewed Y, and those tend to be substitutes. And then people say, and then also Amazon says people who bought X also bought Y. Those tend to be complements. Okay? So we are using that as a kind of weak ground truth for our task here. So that's why I'm showing you Amazon data. Okay, and these are different product categories and their sizes and so on. And this data it's publicly available off of my website at Stanford. Right. So just to show you how well this works. This is different product categories. I'm showing you just 3. This is the accuracy, and this is the error reduction. And this accuracy is kind of computed on a balanced set, but it's not entirely balanced. So these accuracies of random should be around 0.5, but they are not because the way the evaluation works. But doesn't matter. So what's the point? The point is that if you would just do, so the LDA stands for, I will do dimensionality reduction first, and then I'll learn my logistic regression and see how well it works. These are the numbers, okay? And then our system is down here, and these are the numbers, right? So what is 1 point? 1 point is that, if random guessing would give you 60%, we are at 90 plus. If you would just do dimensionality reduction without kind of biasing dimensionality reduction towards link prediction, you don't really do too well, right? So it's really important to bias your topic model towards the task that you are trying to solve. And across everywhere, our accuracies are around 90%. We also did the kind of a user study where we would compare our substitutes and complements from what Amazon gives you as a substitute and complement. And what we found is that substitutes are a much easier problem because it's very contained, right? It's in the same product category, something very similar, very local product. So there we were just a bit worse than Amazon. But then when we compared on the complementary products, right? Products that kind of complement each other, which means you have to go across the product hierarchy. This approach is really much better than what you can do with behavioral data or what Amazon is trying to do, right? But just this is a set of results. I'll give you some examples. Okay, let me skip. The other thing I was telling you before, because we do this hierarchical topic model, I get these nice fine-grained topics. So what I'm trying to show you here is, for example, these are the topics that belong to the tablet cases little leaf somewhere in the product category. And again, these are the words or the features of the product that are associated with those topics. But you can say, oh, I have these heavy-duty cases, I have Samsung cases, and I have other kind of leather-type cases. Or down here, you see, for example, for headphones, 2 of the topics we split at the bottom. You have this kind of high-end headphones and budget headphones. Or for running shoes in your product category, there is just a category of running shoes. We split that. Here I'm showing you 3 examples of, these are the words, these are the names we gave to these topics, right? One is kind of athletic running, minimalist running, and kind of sports shoes, right? So we are able to take whatever you have in the tree and kind of grow it for another level to better understand the relationships. To show you examples, these are some visual examples of these micro categories, right? This is one set, this is the other set, that's the third set. So you see that it's more than just black clothes or something. It's black clothes with a big bright logo in front, or it's not just shirts, it's like this kind of checkerboard type shirts and so on. So we are able to capture these relationships at a very fine-grained level. We can also go and explain user preferences, we can go and explain user preferences in a sense that we can label the edges. And the way we actually can do this is, this is my model for deciding whether there's a relationship, right? We have the model the logistic regression that says, are the 2 products related? And the other one that says, given that they are related, what's the direction? And what are we basically doing is, we look when we have a pair of products, we look what features, what are the phrases that would maximize the likelihood of that relationship, or what are the features that maximize the likelihood of relationship. So we are almost asking, like, what are the few features that give us the most explanatory power for a given relationship. And actually, what turns out to work better is we are using the directedness model, because directedness model focuses on kind of subtle product differences to determine, does the relationship go one way or does the relationship go the other way. If you would be using the relatedness model, this one, then that would be very hard, because the relatedness says, are these 2 products of the same type, so that they are related. But the directedness model is the one you want to use to generate explanations. To give you some examples, in the product graph, this is the node we are looking at. These are some substitutes and these are some complements. This is for, for a particular female belt. We kind of find matching substitute belts, and here are the complements. On the men's side, this is the belt I'm looking at. These are the substitutes. These are the complements. And I could show you more examples. And usually these things are, here it's very easy to know whether whether it's good or whether you made mistake. And our precision at top 10 is usually is around 0.9. While here it's kind of harder to know whether you made a good recommendation or not. And this is also a harder problem. So this is what I wanted to tell you about products. But now, right, what is really interesting is how kind of can we take this technology, or how does this technology work on top of Pinterest objects? That some are products, but not everything is a product. And I show you this graph before of our objects and how they are annotated, and we know the underlying web pages, so we can create very rich feature vectors for each of these for each of these objects. And kind of what are we really trying to do is we are trying to understand how these different objects fit together, so that when a user comes to our site and maybe looking at some object that's related to San Francisco, we are able to actually make very targeted recommendations based on that user profile, that are not just, here are more pictures of Lombard Street, right? But here are some other tourist attractions, here are the galleries with these given artists, here are the sport venues, food you may want to go and eat, and so on, right? So we really want to understand how these objects relate to each other, so that we can give both structured but also kind of user context-aware type of recommendations. And right, one approach we have that I think will get us there is through basically explicitly learning how are things related to each other, right? So here it's not products anymore, it's places, it's food, and so on, right? So that's kind of the idea where this is going, and how you could now start making basically people to really not just be able to save these objects, but actually do something with them, organize them into much more meaningful sequences, plan trips, things like that. Okay? Right, so with this, I'm done. As kind of every talk in the Valley, we end like this. But really, I only have this slide because I wanted to share my paper with you. Okay, thank you very much.
So we have time for questions.
Sure.
I'm just wondering if there are any endogeneity concerns when you do this. So you have a lot of information on demand, like what people want, but you, correct me if I'm wrong, you don't have so much on the supply side. So I'm trying to think that if you're trying to get to the true relationship in terms of whether something's a substitute or a complement, that those supply side movements might be biasing some of the results that you're getting. Do you think that's possible?
I'm not sure I'm not sure I understand your question, to be super honest.
So in economics, you can a really simple model, you can set up a linear regression of a demand function. And you can estimate a linear variable as far as how far things are related and whether the complements or substitute. But what can happen is you have movements in supply.
Sure.
Because companies are always changing around the types of things that they're doing to market their products, and they're looking at a lot of the same data. So a lot of that movement can result in a bias in your estimating variable. And I guess maybe an example that's a little more to what you're doing is, if I got a recommendation to see the San Francisco Giants, that's useful for me, but what might even be more useful is maybe there's a recommendation to go to a really small restaurant that nobody else knows about, or something, because that is information that I really wouldn't be able to get anywhere else. And part of the reason that the San Francisco Giants might come up first is because they're marketed way more. So that's a supply side variable.
Oh, but maybe what I wanted to say is the following, right? The way we think of this is actually we want to have a set of ground truth relationships, and I kind of don't care about supply side. I just care about what is related to what, right? But then when the user shows up, now I can start re-ranking and redeciding what to do and which relationships to invoke and which things to specifically do in that given time, given the supply I have and so on, right? But here I'm really just asking, here's a set of objects. Somebody gave me the some subset of ground truth relations. Can I generalize that to kind of discover the relationships and label them? Right? And now, if I want to use this for advertising, for recommendation, of course I cannot just say, oh, here's a node, here's the other things around it, right? But I can use these things as candidates, which I re-rank depending on what is going on at that given time when I'm making the actual recommendation to the user. All right? Good. Yes.
So when you said your algorithm is to relate objects, and what do you use to identify objects? From what I heard, it seems like you're using labels, meaning words, to identify objects. You say that's a belt or that's a basketball or things like that, right? But let's say if I have an object and I want to be associated with every other object, I can potentially game the system by labeling it with many different names and therefore being somehow associated with all the possible, all possible.
Great point. So you were asking, right? So I would just say, so the question was, I can game the system, right? Because I have these objects. In my case, they are pins, right? Kind of objects are given to me, but each object is described by a feature vector. A big part of that feature vector goes into the description of that object. And of course, if now I add lots of different words around my object, it will be kind of related to everything. I mean, there are ways how you prevent this because you use some kind of TF-IDF type scoring and things like that, right? But still, I think the point is that the feature vector that I'm generating, that's my own. You can try to game it, and I'm sure people will try to game it, but that's then up on me to make sure that I have a clean description of what that object is about. And it's not only about the description, it's also about the features of the image, right? So you could imagine including the image vector in there, like some kind of deep learned features if you want, like that. You could even add in information about who was the user that created that, what's the brand, and so on and so forth, right? So that feature vector, you can kind of put in whatever signal you like, and whatever part of the signal is the most robust from your point of view, or from the point of view of your application. But it's a good question, right? I didn't really say much about how do you generate that description of an object, and that depends on the application you have. Okay, good. Yeah. Sure, go ahead, and then it's okay, right? Okay, good.
The product hierarchy that you showed, that was I right in thinking that was manually labeled, that comes a priori. So how did you associate the topics to that?
Aha, good point. So how does product hierarchy come to it? So because I showed you, or because we started working on this on products are associated with the product hierarchy. That's a given. Everyone has that, right? So that's fine. But how do I associate topics? I don't really, right? All I do is, if you think about when you are, you have an object and you want to determine what topics does this object belong to, and you have this super long topic vector. You don't need to determine how likely is this object to belong to the first topic, second topic, third topic, 10,000th topic. But you say, I'll take the first 10 topics and I'll associate them to electronics. The second 10 I'll associate to books. The third 10 I'll associate to kitchen appliances. Then, under electronics I have gadgets, I have audio, video, and I have TVs. So, I'll take the next 10, I'll associate here, next 10 there, and so on. So when I'm trying to decide where to put this laptop charger, I'll just look at the topics that are associated with these particular nodes in the hierarchy that go down. So this means that naturally, the electronics topic, when I determine memberships to it and when I determine what words are associated to it, for all the electronics products, I'll be sampling those topics. But for chargers, I'll be sampling the electronics, but only for chargers I'll be touching the charger topic. So kind of how you associate doesn't really matter. You just, before you start training, you say, you get 10 topics, you get 20, and if you feel you are running out of topics, you can just kind of, during the sampling procedure, you say, oh, here are 3 more topics, go fill them up, right? But then products, belong to different types of the different parts of the product hierarchy. So certain topics will be selected for different subsets of products. Right, the electronics topics will be selected for all the electronics products, but the chargers topics will only be selected for chargers. Right, so we'll naturally be fitting chargers only to chargers topics plus everything above, while the electronics topics will be very general because all the electronics topics, all the electronics products will try to be fit to the electronics topics. So that's how you get a natural kind of hierarchy. Of course, you could say, I want to learn this hierarchy, but then it becomes even more complicated. So here, we kind of exploited the hierarchy we were given. All right, good, thank you. Yeah.
So you kind of asked my question.
Sorry.
So, on the, for the product hierarchy, does the depth of the tree play a role here? Because, or something like how can you define a certain depth? Yeah, optimal depth when you are going down the hierarchy.
For the experiment I'm showing you here, we just used whatever is the Amazon hierarchy depth, which I think is maybe 4. It's 4 or 5, right? So that's how deep we go. And then we didn't try saying, oh, let's prune that, because you don't want to prune. You want to have this fine-grained resolution. But the problem is these product hierarchies is that they are not fine-grained enough. So to the leaves of the product hierarchy, you associate quite a few topics, because then that allows you to take all those laptop chargers and kind of find micro categories of the category laptop chargers or whatever. So that was kind of the idea why you want to extend it, because you want to kind of at more fine-grained level understand what products kind of belong to the same part. Sure.
Do you leverage the connections between the actual users somehow to inform how you do the categorization and the topic extraction?
That's a great question. No, we didn't do that. So we are not using user information or who reviewed what type of information to try to use that as a signal. That'd be a very interesting signal. One thing that I didn't mention, because I thought my talk will run long, was one thing that turns out to be very important in these types of applications is that you have no negative examples, right? You have no negative data. You have no data what is not related. You only know what's related. So then the problem becomes, how do you generate your negative data? And it turns out that, right, the first thing you say, I'll just take some random pairs of products and that will be my negative data, right? But then the problem is that it's kind of far too easy, right? You are learning that laptop chargers and, before I was saying baby diapers, they're not substitute nor complementary, right? That's kind of fine, but that's too easy. So the problem becomes that then you don't learn anything. So what we were quite careful about is that when you are generating negative examples, is that you really kind of find pairs of products that are relatively close in the product hierarchy. So they are still quite similar, but they are not related. And that was kind of the trick to get the learning going. So that is hard. We didn't have anything principled there, but that was an important step, is how do you generate the negative instances? And sampling them at random won't give you anything. So you have to be smarter. Sure.
So you mentioned earlier that you would try to show how you combine the relatedness with the the complements.
Mm-hmm.
When you make recommendations, how do you decide to combine it?
Good question. So how we are deciding now to in recommendation which thing to actually surface out. That is basically that is where the user features come into play and the context in which the user is. Right, so that this blender or whatever we learn based on the context in which the user is and based on the very kind of short-term actions that they did. Right, so in some sense, what this allows us to do, it allows us to do this to get this interesting diversity in recommendations, because we can switch very quickly to say, we switch from substitutes to complements. Right, we generally would start with substitutes, but then once you've seen a couple of clicks or something has been chosen, then you start kind of shifting towards complements. Yeah.
So do you look at time between, so you can see something's accelerating and people are combining these two together over a short period of time, so it's moving up further, and do you track that at all?
I mean, the way we are, so this is, I mean, big parts of this are what we are currently thinking about. But the way we are thinking about it, or our current thinking of it right now, is that this shifting is something that's very kind of short term, right? It's inside the session. It's not that you'd say the first half a year I'll do one, and then the next half a year I'll do the other. So these switches should be much more dynamic and much more short term. So we really kind of, yeah, the way we think is it should be kind of in the, I know, in the same session, same day, same project, whatever that means. Good question. Yeah.
Use special way the time dimension, like if you use all two things at the same time, it's probably use the same way.
We haven't done that, but that's a good idea. It wouldn't be even like. It wouldn't even be hard because you could just throw yet another time-dependent feature somewhere in there, and the mod will pick it up if it's any useful. We just haven't done that yet, but it's a good idea.
Have you got any evaluation of how often topics you find as explanations of direct relationships are actually, seem to be accurate to people?
I think the point there is that the way we are planning to solve that problem, actually we haven't tackled it yet, but the plan we have, or the way we think about this, is to kind of combine learning with some human curation, right? So I don't think I'll ever, I was showing you these things, right? But even these topics that we had here, they are just words, right? So we need to do something more, right? So this is not an explanation, right? So what we actually do, we have some step where we do the phrase extraction, and then we kind of label or cluster those phrases, and for each of that little small cluster of phrases, we say here's kind of the annotation we find. So we have kind of a two-step process that's done on top of the topics we extract through human curation. Yeah.
Yeah, I was wondering that, one of the kind of, from what I get from the complementarity that you learn, one of the ways of sort of extending that would be to sort of surface the recommendations as an ensemble of objects that are related to each other.
Mm-hmm.
So say, you have a shirt, let's say this tie will go with it, this belt, this wallet, this shoes. So have you thought of like surfacing recommendations like that, which sort of completes a set?
Exactly, that was my slide number 3 or whatever, was my third use case, right? I showed you this San Francisco hipster outfit, right? Somewhere here, right? Yeah, this one, right? Where's my? Right, so yeah, you can easily do this, right? And this is not so hard to do because all you have to do is kind of find a template that says, combine these nodes of my product hierarchy, right? So you can just write a template, and from now on you can start recommending wardrobes, right? Because you say, I want something that belongs to shoes, something that belongs to male pants, and something that belongs to male shirts or whatever, right? So it's not too hard, and this starts to work really well when you start also using image features.
Yeah.
Then the color and the patterns come in, and then it works really well. Yes, and then sure, and then it's you. Yeah.
So once you have users using these recommendations, how do you incorporate all of that data back in as training or as features or whatever you do?
We just had this discussion before. Can I summarize what we were discussing? Sure. So what we were, so I don't know. What we are doing right now is. As we are deploying these things, sometimes you get to see that the data that comes back is kind of like, if you learn your system over the data that came back, many times your performance will degrade. Especially, we were discussing before, if you have this kind of closed loop systems where it's your recommender system that is generating you the data, right? So you would want some external way where your things get perturbed a bit, or some other way where people can, give you some information so that you can really kind of learn from data that is what you get to see in the wild rather than what you showed to the user. those I'm not there yet to tell you what happens in this particular case. Right now, I think we have enough other kind of additional sources of data where we are not suffering by kind of overfitting or getting confused because we are learning from the same data that we served. Right, because the problem is the following, right? You have this huge catalog, you are only showing this part of it, and then you think you will learn how to separate good part of it from bad part of it. But then you have all these things you haven't shown, and then your classifier will say, no, just go here, right? There is all this stuff, who cares, right? So you wanna use all these that user didn't even see and say, no, this is also negative, I just kind of didn't even show it, right? So how do you do that in a principled way? That's a very good question. Yeah, good, yes.
I'm wondering about what is the consistency of success between different product categories? Like, do you find that it works really well for some kinds of products and not for others? And like, how do you account for that in terms of like, features of the categories?
I think that this is an excellent question. What we find is the following. It works like, for example, for electronics, it works well. I could show you some examples, right? But electronics, it's very clear, it's very clear, right? For camera, there are cameras, and if it's a Canon camera, then it should be Canon lenses as complements. You should not put a Nikon lens there. So those are kind of easy, but from the model point of view, also hard, because you just doesn't know, yes, here I should be sure to match on this particular feature. But those are easy to fix. So in electronics and things like that, in these hard categories, we make some mistakes, and those mistakes are obvious. Where this works well is in this kind of soft cases, where whether it's something like clothes or shoes or fashion, where it's not clear whether you kind of made a mistake, but it kind of finds these soft types of relationships that are much more subtle than saying, no, you have to match on the manufacturer brand, otherwise you cannot be matched or whatever. So the place where we see it works really well is in this kind of softer, fashionable products, rather than on these kind of technical things that either fit together or don't. Good question. Yeah.
So it seems like the model is really trying to optimize for relevance. Do you care about popularity at all? Like in traditional collaborative filtering, popularity plays a big role there, right? So, for example, if some style of dress, is getting popular,
yeah,
do you want to, take that into consideration?
Sure. So the question is about popularity, yes, but I think of that as kind of independent dimension that I should take care of at the time when I'm ranking, right? What I'm interested here is just to understand how things fit together. If something is getting popular, or if I have more signal about it, sure. I mean, in my case, what will happen is that, sure, for rare products, I'll have little features, little description, no reviews, things like that. But we were even trying with products that had no reviews or products that had very little data, but there's always something you can find to make a good description of the product. So cold start in this respect is not a problem. Popularity sure gives you more data, but the other thing, to really answer your question, in graph creation, I don't think we should worry about popularity. I should worry about that, at a given time when I'm serving to the user, based on whatever I have. Sure.
So you said at the beginning of the talk, assume you can do all these pairs of figure out if things are complements and substitutes.
Yeah.
So how do you actually scale that when you have millions and tens of millions of things to compare?
Sure, good question, right? So in reality, we cannot really compare all pairs and score every possible pair. So for products, what you can do, because you have a hierarchy, you can rely on hierarchy to again not go and sample.
But how do you do that for the complements where you might want things that are other parts?
Exactly. So complements are harder. Substitutes are easy. Most of them are just in the same little part. But for complements, the trick is to go far but not too far. right? So you wanna go, I don't know, one level up, down, 2 levels up, down, things like that. So there, this is how we are expanding, and we have this kind of classical candidate generation step and then a scoring step. That's how we solve it. Yeah, I don't know whether there's a better, like there's an elegant way to do this. You had a question? No?
Yeah. Actually, so I was wondering, you use one single embedding to train multiple regressors from this. Did you consider trying to find modifications of that embedding to specifically for different regressors and see whether different embeddings for different regression could lead to better results?
So the question is, we started having multiple embeddings, but then the problem becomes you are not sure which embed, like how to whether you are using your data well enough, whether you have now these different ones. So what is now, if you want to do explanations, should you use, what should you use, and so on. So we thought it created too many problems for us, so we rather decided we'll have one embedding but separate models for each relationship type, and this way we are kind of using data in a more efficient way. That was our first approach. Hard for me to say more. Okay, good. Anything else? No? Good. Okay.
That's time. Let's thank our speaker again.
Sure. Thank you. Thanks.
Terry.
Hi. Hello.
I'm here to
Oh, really? Okay.
The one just enjoying studying like
It's finding the majority. Yes.
So what about I
sorry. Weird fashion things. I'm just like, here is what this is. Now if you one of our friends will together, you might get, but I probably won't figure that out, right? So it's a good question. How would you now go? How far can you push personalization, especially for kind of weird or very unique people, where their notion of substitute components can be very different from this objective definition. I don't think it's a good question.
what about like it's not like spending from the
Sort of. That would be another approach to say to go to be able to find this kind of personal type of relationship. That I think would be an interesting.
I'm with NVIDIA. And I work with the deep learning. I know it's usually when you get
We use a lot of different some kind of super cool things.
And then think about like that, and then recommend our system. So I usually like all your decisions, make all based on recommenders. Apparently you're not doing it. So I was
Thank you.
I'm contacting that.
You guys can walk side by side and have
work together.
Like it's easy They're like like everyone likes them. Yeah, I probably also like it. But then I was like, well, I'm like, people think like thought I'm like this. Like people also like things that are not popular that I want
As I said, I haven't seen several sides.
I'm actually in San Francisco. Data analytics and right, so that's why
Yeah, I do business development. So my main job is basically developing the ecosystem. Startups and like big companies that are using these versions, making sure they're developing a platform that we also support on our side, especially technical
So we are doing this to develop products. We are doing this
the beginning of the supply chain, more like product features, making sure they're developing this.
There is this method for one. Basically, you can have a structure where you can have 1,000 word long queries. So I have a product that's a query, and other products are not like that. And I can way that more complementary. So you can do that overnight in real time. 10 so that's what we do to another option we can do. Even though we did lots of very fine
Sometimes third-party organizers and they just use the Oh yeah, yeah.
I never see that.
But it's if you need it, I can share the link. By default,
Yeah,
wait, why target?
The first investment. So this time we do No, I'm on machine learning.
So we use machine learning terabyte of memory because the model is big. So we keep that just but it's just but that's not expensive. Terabyte of machines. Yeah, no. My group was able to take care of them. So it's like using
But the meetup, the event was
Actually, these organized by but partners.
Does Jiggy even have 1 year yet? Maybe today you just say something about you see them very serious.
Oh, you need to do content based and you put content.
Work with the deep learning team
But those are,
and we were willing to engage with Netflix, with the guys that are doing technical work in this area.
Yes, I was probably
We've been working with you guys before, so we just...
Oh, maybe a different team.
Take some notes. So what happens is that there's a ton of stuff for us to follow up on, so we just got this project.
Oh, you did? Yeah, it's great to engage. We're developing a lot of software as well, and those libraries. And so we wanted to know what do you guys want? What type of features would be interesting to have? What's the next challenge? We want to be able to tackle that and give you guys
no, I manage
We're about to launch and we want to see what the next feature should be. And early access to the library. For us, at this stage, it's very important that we recognize that much more expansive engage with we need a bigger crowd. What others do well. Very nice. I'll be probably the main point of contact on Netflix. It's a tough
I spent about half an hour.
Definitely would like to engage.
I didn't move the family.
Yeah, and as I said, it's actually in the research guys.
Very nice.
Thank you very much. Very nice to meet you. Sorry for coming in so late. Anyway, at least I could meet you guys.
How's the new thing? Well, so we work on the
exactly, and that is
your website was quite fun on those. Fun little 4 slides.
So I think that's even a feature to the title. So there is a paper. Maybe you'll find it on the web.
For offline analysis, I mean,
send me email.
Maybe a little bit.
Okay, great.
You know, a bunch of internal reporting tools.
Yeah, hi.
You know, and Spark.
Would not be available.
Sure, I can.
We collaborate with partners, so we'll partner with science and algorithms, which has
let's talk to
Oh, okay.
we work Sure. So we collaborate with them, you know, so they do some
I think it's fine. I think you should try because we'll take their code.
Okay. Yeah. So it's going to be
it's gonna be and also the video gonna be posted as well.
Okay.
Yeah. And I'm gonna send you the link as well.
Sounds
for the
great.
video.
Okay.
Yeah, thank you for coming.
Yeah, no,
thank you again.
Thank you for coming.
It's really awesome. It's really awesome.
Maybe I will be fast.
Yeah, I mean, trying to hire people over here. Sorry, you're trying to hire people? No, I'm joking.
You show, I think it's good people see, oh, you know, everyone wants to give me a job, right? No, I mean, of course I'm hiring all the time for jobs. If you need a job, let me know.
So sometimes
Yeah, cool. But I mean, I had no expectation. I didn't bring any swag or whatever. I didn't give them water bottles. It was nothing like that.
Oh, yeah.
But of course, we are always. Yes.
higher end too, if you are interested.
Yeah, it depends on the show.
Whoever doesn't make it with us will say no to those guys. No, it's
You know, batch jobs, things like that will be,
Oh, hi, yes. Hi. We said we talk a bit.
I'll be sure.
I think I'm ready.
So you're the organizer?
When are you throwing us out? In 5 minutes?
Great. No, I think I saw you at like a couple of years ago.
Oh, yeah.
Yeah, it was a great talk.
Happy with you.
Yeah. So that was organized by
So usually we here?
Yeah, because I saw you.
So this is the first time this thing is involved. I mean, there's other
Are you also? I was on the peninsula. Yeah, so by commute. This is really far for me because I have to commute down here.
I know that Scalability is far away from
I think a lot of people say like traffic.
You have my email address.
Yes, exactly. Okay, great. Thank you.
Oh, hey, Joe. We're gonna talk. I did something similar to with Walmart.
Oh, really?
It was really tough.
So were you working at?
We're like,
Yeah, I work for
I'm consulting with them. And
Oh, I see. Okay.
it's very interesting with purchasing.
All right, no.
What do you mean?
Well, I'm a
That's
business
the problem. I
intelligence.
tried to solve it. We took like Twitter data back in the days.
I'm definitely interested in
Pretty cool.
Okay, now we showed this to Walmart and they were our customer immediately.
Oh, really?
Yeah, that's my care.
Oh, so this is the same thing like
Maybe
I
you evangelize them.
Yeah, I did this for them like 2012 something like that. 2013.
Thanks.
Okay, can I connect with you?
Sure, yeah. Okay, cool. Okay, thanks.
So what people like suggestions is on Netflix. That's supported by yeah, that's
Sure, it's the best way to get in touch. Okay, so we live in Stanford computer because I have.
Yeah.
And they are
okay,
a
nice to
way
meet
for
you.
companies to connect.
See you again.
And I'm sure IBM is already part of that, so we should just reach out to Stanford Computer Code. It's called Computer Code. And then they organize events on campus, you can job fairs, things like that. That's the best way to connect to students if you want to hire. If you want to connect with research groups to do research, this way kind of hire PhD students. That's deep science.
So we're more focused on user research. We want to see how they work, how they learn to become data scientists. So I know we have the hiring as well.
Sure.
We're more interested in how they become data scientists.
To solve the problem. We can't share that side.
But I'll look into that. Maybe I can send you an email, tell you a little bit more, and then you can see.
Sure, and I can see. Okay, sure.
That would be great.
Yeah,
Thank you so much. Nice job.
Hey, I'm Ryan. I work for Genentech.
Oh, I see.
I'm doing like data analytics for their marketing team. I have a background in this field, but I've been in this field so forget most of the stuff. The question is, how do I follow up with you or take more courses from Stanford to learn more of the advanced stuff?
I mean, we have this kind of system. It's just running right now. So just go to basically the thing to remember is mining data sets, or go on my website. There is a data mining book with lots of recommended system type things up there. Free. There are lectures, there are videos, there are slides.
Okay. So how do I think? Okay.
Just search my
where you know? Oh, okay. Awesome.
Just search my first name.
Okay.
Just so you understand.
Okay. Awesome. That's good.
I actually took Jeff Altman's class.
Yeah. This was a few years ago.
Yeah.
341. Yeah.
I'm actually working at video now. You met Arnaldo.
Yes. I met him.
So he's focused on this dev. I'm focused more on academic side. And so I work with like open source developers. I just want to see how
I'm sure you are working with our vision people.
Yeah, exactly. Yeah, my have connections to Stanford too. Really liked your talk, and of course, feel free to ping Ronaldo on any.
Sure.
You have software questions probably.
I see, so you're not yet in machine learning.
Well, we are exploring some
Data
things right now, deep learning
engineering,
for
data
Which
quality,
framework?
Are you doing it in C++?
Yeah.
Lots of ETLs, feature engineering.
Okay.
Yeah, absolutely.
Sure. Yeah, thanks a lot. Yeah, thank you.
Thank you.
Great. Pleasure meeting you.
How are you?
Hi,
Tim.
I'm Ryan.
Nice to
Nice to meet you.
Good. So, are you a machine learning guy?
I'm a data scientist. I work for Genentech.
Oh, okay.
I do like marketing analytics with understanding their customer.
So you build models based on
Yes, sort of doing models, tracing how understand how the customer, which type of drugs they like, what kind of experience do they prefer, one way or the other.
Yeah, it's the origin of A/B testing. It's the medical field. It's where it all pioneered.
Yeah, sort of. It's the A/B testing used in marketing. That's one of the.
So do you have experience with machine learning, or are you, is that something you're interested in?
Well, I learned them before when I was in my master's degree, but then after I start working, I become more, I guess, work in the business side, and therefore forget a lot of this stuff. But I would say I have some background in machine learning.
So,